Welcome to week 7 of the basic soil science class. Hope you're having a good weekend. We have finished some interesting material. The group index that you all did, in my mind, well on. Uh, just before I forget it, and I think I've mentioned it in since since we've done that. If you guys will show your work, I can give you partial credit, like on the midterm when we got to the final uh, question. I feel like some of you were close, and I did give some partial credit for that. I compliment all of you on the fact that you did. Uh, you were coming up with some correct answers. It was it was good. So good job goes out to all of you. We're going to continue on into this chapter 2, the engineering properties of soils. And want you, I think it's in your reading or your instructional material, to read this section 2-1 on soil types. Now, you're just finishing or in the middle of uh, are the week 6, which has to do with, you know, a little bit of types of rocks. And then, so of course, that made types of soils. Well, this is going back to the NCCER soils module that we used. I forget which section that was in, but we're going to be talking about particle size again. A lot of these things you've had, but have some things highlighted in here that will help you as we begin to classify soils. We've been moving in that direction, going through a little math, a little knowledge, the where do the soils come from. So now we get down to the nitty gritty. And as we move along, we'll begin to get into testing and some more things like that. Now, some of these things, again, and I may have said it before, the calculations are just way, way beyond the scope of this program. But we can talk about the types of tests, the particle phases, is a pretty simple deal, but density, relative densities has some complicated formulas, but we'll look and see what we want to fool with. And the main thing we want to get out of it is that this is the apparatus that you use. This is the results that you get, and here's how you might interpret results, but what it tells you about the source. But for now, we're into classification, and we will classify some soils. That's just not a whole lot of people you meet on the street in construction that know how to classify soils according to the two uh, widely used classification systems, which is the uh, American Association of State Highway and Transportation Officials, the AASHTO, and the uh, Unified System for Soil Classification, or US USCS, Unified System for Classifying Soils. So this chapter touches this, and I mean touches on uh, the unified system, uh, and we'll get into how to prepare uh, to classify in the AASHTO. The first thing we'll do is learn how to calculate the necessary parameters to develop a particle size or grain size distribution uh, graph or chart. It's done on what's known as SimLog paper. If you get a chance, I'll be showing you some. Actually, it's not that far away. If you get a chance, I have downloaded some to play with and ordered me some because I'll be doing this again in a year. But Simlog paper is. Let me just talk about that so you'll know where we're going with these little calculations. There we are, right here. Simlog is used when you have a whole bunch of numeral values, numbers to put down. These spaces are take in consideration that you're using what is widely used in engineering. It's called log 10. These things are based on exponential powers, like, and I just don't want to go there. There's no need in it, but we can really kind of see how to read this thing. If you, and this is our what we'll end up knowing how to plot. This 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 is a particle or grain diameter, log scale, grain size distribution curve, and these will, once we get this, we can move on to those coefficients of uniformity, coefficients of curvature. I've seen what you can do with some complicated math. So we're going to keep moving on into the Atterbury limits, plasticity, and all those things that also go into classification of soils. But for now, let's just take a quick look at this. These are sieves, and you should know what I'm talking about when I say sieves, because you had two videos that talked about them, and we may have mentioned them before. But the main sieves that we'll be using will be a 3/4 inch or 3/8. The number 4 sieve, which I forgot what it is, but give me a second and I can tell you that's 4.75 millimeters. The number 10 sieve is 2 millimeters. The number 40 sieve, the higher the number, the smaller the sieve. The number 40 sieve is 0.425, and the number 100, I don't think we'll use it, but if we do, it's 0.150 or 150 thousandths. That's how many holes there are per inch in a sieve. So some of these things are like smaller than your window screen. The number 200 sieve, which is not listed here, but we'll be calculating it on this little dotted line. I'll probably put it up there. It's the smallest one we'll be dealing with, and it is 75 thousandths, 0.075, and it really looks like a piece of claw. But the real fines, the clays, some of the silts might, but usually the silts and the clays won't go through it. And of course, none of the coarse grains will. Okay, look at this. In this case, as you can see, it goes to 100, so we're going to read it from right to left, and there's 10 intervals in here, and this is an easy one to look at. This is 1,000ths, 2,000ths, 3,000ths, 4,000ths, 5,000ths, 6, 7, 8, 9, and 100th. So that's 10 thousandths that we moved over here to make it 100. Moving on, when you're at 100th, you go to 2, 3, 4, 5, then there's another, then you're at a 10th, and you go on to 10 of those, and you're at 1, let's call it millimeter. That's what they usually measure. That's the size of the particle. And this one would go, see, this is 1 unit. These were decimal point, but this one would be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. It's just a convenient way to get a lot of information in a small space. I don't think this will give you much trouble. And as we move on from here to get our Atterbury limits, we'll be looking at the 50% passing and see where it hits this curve. I think the 10% will be used to determine some things like liquid limit, plastic limit, and things like that. So going to back up to the beginning, and that looked like the end, but it's not. There's a sample of the AASHTO, and we'll get to this in just 1 minute. This might be a little bit long, a little bit longer video than normal. It's more of a class, but you can read it at your leisure. Here we go again. So I have highlighted some items that I want you to see to make sure that we're focusing in on cohesionless and cohesive. This is coarse grain stuff, cohesionless, and cohesive are your silts and clays. And then there's the organic that is not beneficial for any kind of construction use as far as I know. Good for gardens. And cohesionless soils, they don't tend to stick together. That'd be your gravels, your coarse grain. And I want you to understand this because of the terms. You'll be hearing this from this point on and have heard it up to this point. So the cohesive are very small particles. The particles tend to stick together. They're sticky, plastic, crumbly, compressible. But there's 3 common cohesion-less soils, and that's where we spend a lot of time this week. The 3 common types are gravel, sand, and silt. This gives you particle sizes for gravels. It's not too important that all of these are memorized. I will probably put together a short quiz on some of this stuff because it's all important and it's all relative to the foundational information for where we're going. Then it talks about the gravel and sand can be classified according to particle size. Silt has really, really small things. Clay is even smaller. You have to see the particles in a microscope for clay. And here it starts to begin to talk about the American Association of State Highway and Transportation Officials, the AASHTO it's called, and the Unified Soil Classification System. The given in table 2-1, but they're not going to give you much. We'll have more than that when we start classifying. It's clear from variations between these classification systems that boundaries between soil types are more or less arbitrary. Not sure what they're talking about that, but when you go from one, they may or may not be too different. They can be categorized in terms of grain size. 2 are coarse grain and fine grain, and that's what we'll be dealing with a lot. And this here is the 0.075 or the number 200 sieve, and that's what we'll break these down into either fine grains or coarse grains. Actually, in the AASHTO and AASHTO, anything larger than if most of your material is more than, well, I'll wait till I get there. So the number 200 sieve is kind of the dividing point for classifying these soils. In the AASHTO, I'll just go ahead and say it. The granular materials are 35% or less of the total sample passes this number 200 sieve. I think we talked about this before, but less than 35% would be classified as granular materials. Now, the first thing you do when you pick up and I'll show you one here in a minute when we go back to the other view. Uh, that'll be at the top of the chart of an AASHTO chart, and then you'll know that if that's more than 35% of the material, if it's more than 35% of the total soil sample, then if it passes the number 200 sieve, you're in silt and clay materials. So you just get the granular materials, which are on the left of the chart and more predominant, out of the way, and then all you work on is the silt and clay materials. So that's where you'll always begin. And you've seen, I think, a sample of an AASHTO chart with, I know, with the TA, the one where the guy that drew the little sieves. Pretty good explanation of the sand and gravel and clays, and then he used that classification system, like does this like liquid limit and what passed the number so and so sieve, if it would less than or equal to, etc., etc. But you could see how he moved to the right. I don't remember what that soil was classified, and I don't remember if he quite finished it or not. But you did get to see a chart, and when I get over to this other camera, I'll show you an AASHTO chart. So review this with in mind that you'll be seeing using or relying on this information to move forward. Silty soils, kind of a broad explanation of that. Oh, here's a sample of what they're trying to do is show you a section of an AASHTO and a unified soil classification system in terms of gravel, coarse sand, and medium sand, and how each determines the gravel. If you take a look at, I pretty much remember these, but I got notes here. So gravel is material that passes a 75 millimeter sieve and is retained on a 2 millimeter sieve. So the 3-inch passes that, but it's retained here on a 2 millimeter. 2 millimeter is a number 10 sieve, and that's AASHTO. Now I can kind of say that better than I can do it this way. Just listen, material passing the 75 millimeter, which is 3-inch, and is retained on a 2.00 millimeter, which is a number 10 sieve. That's gravel. Coarse sand passes the 200. Where am I? Coarse sand passes the 75, but is retained on the 19 millimeter sieve. The same deal, 3-inch here and 3-inch here, but this is retained on the 19 millimeter, so the 3/4 inch can't get through. This is on the 2 millimeter, so this is finer. And let me go over here to coarse sand, and then I'm assuming fine sand. Coarse sand for AASHTO passes the 2, but is retained on the number, passes the 2 millimeter, which is the number 10, and is retained on the number 40 sieve, which is the 0.425 sieve. That is coarse sand. Remember over here, it passed the gravel passes the 75, which is bigger, and is retained on what the coarse sand goes through. We're talking sand versus gravel here. So in the USCS, the coarse gravel is a bit like that, but it is retained on the 3/4 inch. They go straight to the 3/4 inch and passes the 3 inch and is retained on the 3 inch. And then they have a fine gravel that is 3/4 inch retained on there. And then their coarse sand is passing the 4.75 sieve, which is the number 4 sieve, and it's retained on the 2 millimeter sieve, which is the number 10 sieve. And it goes on and on and on the same way. And down below is much more information. This is just a snapshot. And this you would see at the top up here about the information of granular materials of 35% or less of total sample passing the number 200 sieve. And then over here where it's got fine grain, there would be a note saying silt and clay materials like fine grain is more than 35% of the total sample passes the number 200 sieve. So that would be the general classification and would help you move, not try to calculate things that you don't need to calculate. Now I'm going to move into this grain size analysis deal. Let's see. Organic. Okay, so the soils are categorized as cohesive. We've said that, and generally implying a sandy soil clays. Nothing new is up until you get to, I believe this picture actually was in the NCCER, and when I read all of this information leading up to where we are that I just went over, if you've already seen that, but still go over it. Here's a standard sieve numbers openings, and I was hitting around and on some of these. The 4, this is all in millimeters, and as you can see, this is a real important one right here. This separates the fines from the granular, so it's important in 2 or 3 different ways. That's the main one. And the guy drew some pictures. He was a TA for, I forgot, some school. I used his video. But you can see where you would put all of your soil sample would go in here, and you stack these sieves, and they are put on this. If you've ever been into Home Depot, they want to shake your paint, and they got this thing that shakes the paint, and they clamp the paint can in there, and it shakes it and keeps you from having to stir it all up. Same thing here. They get put the soil sample in the top, and it's clamped on this paint shaker, just like in the Home Depot, and it shakes that material. And there's a certain amount of time you're supposed to shake it. But anyway, and you can see the fine particles are going through the finest sieves, and then what makes it all the way through this number 200 sieve goes into the pan. And that, I'm telling you, that's some real fine stuff. Let's see. Moving along. Moving back. This looks like a grain size analysis. So it's telling us that the properties are greatly influenced by the size of the particles. In the most cohesionless soils, distribution of grain size can be determined by sieve analysis. That's this. It's similar to it. My grandmother used to do a lot of baking, and she, made things from scratch. And she had a flour sifter to sift her flour through and to make the flour become a little bit more finer. And I guess it was easier to mold into biscuits and whatever. but that was always done. Table 2-2 will get there within this range, can be classified according to U.S. sieve size. That's this guy right here we just looked at. Now, all the end of the at the end of the procedure, that's shakenness, the soil particles retained on each sieve can be weighed and the results presented graphically in the form of a grain size distribution, curve. I've talked about Similog plot, and we'll get more into that. We have an example, and the example is a problem, but it illustrates the analysis of the results of a sieve test. Now, the second video you watched, I believe this lady went through the same exact thing as you're going to go through here. And I will have keep in mind, all of this is done. You need to go through it. We're going to walk through it, and then I'm going to show you how I do it to make it easier on me, sort of like that lady did with the made up her own little table and so forth. But let's read through this, and here's what's important. You've got to know that your soil sample, this is the total weight of the sample that you start with. So when we get into the percentage, we're going to be dividing this figure, which is the mass retained, divided by the total. Where's that total? 2,000 times 100, and that's going to give us the percent retained, and we'll get to that in just a minute. So this is what's retained. Nothing made it to the in 3/4 made it to the nothing stayed in the, I'm sorry, in the 3/4 sieve. 158 grams was retained in the 3/8 number 4 sieve. There was 308. Number 10 sieve, 608, etc., etc., etc. And then 8 grams made it all the way through everything into the pan, and those are what's called fines. They look like powder. So a grain size distribution curve for this soil sample. This is your solution. To plot the grain size distribution curve, one must first calculate the percentage retained on each sieve. The cumulative percentage retained, and the percentage passing through each sieve. Then tabulate the results as shown in table 2-3 right here. So these are all your answers. This is what you're going to come up with, but you need to go through this problem. So you're given the total sample weight of 2,000 grams. The percentage retained on each sieve is obtained by dividing the mass, that's like 158, the mass by the total sample, which is 2,000. So in the case of the 3/4 inch sieve, nothing was retained. So on the 3/4 inch sieve, 0 grams divided by 2 grams times 100 is 0%. So there's your percentage right there. Let's move along. This is part of the problem, but you'll see that they're not going to work the complete problem, but this is the first thing that'll catch your eye. You keep doing that through all the sieves. So I kind of lost my play. Oh, we're right here. This is the 3/8 inch sieve, and if you go right down, there's another. There's a couple of places you can get this. In the 3/8, there was 158 grams retained. So we take that 158 grams, we divide it by the total sample size, 2,000 grams, and we multiply that times 100%, and guess what? That gives us a 7.9% retained in the number 3/8 in the 3/8 inch sieve. So we move on to the number 4 sieve, and look over here. The number 4 sieve mass retained is 308 grams. So we take the 308 divided by 2,000 grams, multiply that times 100%, and 15.4% was retained in the number 4 sieve. Let's see, 15.4 in the number 4. And I think it does at least one more. Therefore, the column 4 equals the column 3. Column 4 equals the column 3 divided by the 2,000 should equal 100%. Now, the way you get that is get the go back here, get this, the total of the column 3, and divide it by the column, what did it say? I forgot. The 4 is the column 3 divided by the total mass. And that's what we were doing. So the next step is you'll go through and you will get all of these sieves. The 1, 2, 3, 4, 5, 6, 7. There's 7 sieves that you have to go through. They don't go through all of them here, but it's the same thing over and over. And then once you have done this this cumulative percentage, after you've done the percent retained, you do the cumulative, and it gives you some examples. Take, for instance, the cumulative percentage retained on each sieve is obtained by summing the percent retained on all coarser sieves. Thus, the first one, cumulative percentage retained on the 3/4 inch sieve is 0. There's nothing to add to that. 0. The cumulative percentage retained on the 3/8 inch sieve is, where's the mass retained? 158, right? Let me go down here. 158 divided by 158 divided by 2,000 gives us 7.9%. So we add it to the 0%. So 0% plus 7.9 equals 7.9. Move on here to the number 4 sieve. The percentage retained on the number 4 sieve, we can go down here and see the percentage retained is 15.4. Zip back up here and put the 15.4, but we have to add it to the 7.9. So the cumulative percentage retained on the number 4 sieve is 23.3%. And we continue to do that. One more it gives you is on the number 10 sieve. Let's take a look at that. According to their calculations, the percent retained was 30.4, so we've got to add that to the 23.3 in the cumulative column and get 53.7. So number sieve is number sieve. The number 4 sieve is 15.4 plus 7.9. That's this up here equals 23% so far cumulative. Then number 10, when you go down here, look at the number 10 sieve, you'll see that it had 30.4% retained plus, I think we've already done this, maybe not, 30.4 plus 23.3 is 53.7. I think we did that already. But you get what I'm saying is you just take whatever your percent retained is, and then you add what the total cumulative percent from the coarser sieve up here. And you do that all the way down through there. Once you've done that, you've got to get the percent passing through each sieve. And that's what's critical. That's what all of this is about. Like that gal said in the video, if it was a shortcut, we would start right here. This is what we'll be plotting our curve with. But we have to calculate this based on the cumulative. So there's a little, I can just throw this out here. Let's see what it says. The percent passing through each sieve is obtained by subtracting from 100% the cumulative percentage. So look at the cumulative percentage right here. The cumulative percentage is 0. 100 minus 0 is 100. On this sieve, the cumulative percentage is 7.9% on this 3/8 sieve. So 100% minus 7.9%, that's the percent passing, 92.1. On the number 4 sieve, the cumulative percentage was 23.3%. So we take 100, 23.3, we take 100% minus 23.3, and 76.7% is passed. So you see percent passing. So far, so good. We said 100, 92.1, 76.7. And if you go down through here and do this like 53.7, 100 minus 53.7, 46.3. Now, when you get through, add these up, you should have 100% right here. That's just, if you don't, you need to go back and see, check yourself. Now, I'm going to switch my cameras, and I'm going to show you how I do these. I do these more like that lady that you saw in the video, and it's just easier for me. If I'm lucky enough to change cameras on my video software. Let's see. There it is. I have this pretty much the same information here. If I can get it right. I made this chart myself, and you can do this freehand. Just bored one day. I just listed all of my. See, I need my mass retain. Where's my pencil? Here it is. I need. This is what I need. Right now, I'm not too much interested in this. When I start labeling my grain size distribution chart, I will be interested in exactly what these openings are. But here's my sieve. Here's my mass retained that we used earlier. And the way I did it is the way I like to do it. Here's the ones we'll be using for the chart. Don't think I can get my whole deal on here. So let's see. I don't think it's going to let me. Anyway, we'll work through this enough that I can get you started. This is the way I do it. Look at this. So we got these sieves showing. If you look up here, these are my mass retained. And on the 3/4, 0% retained. So go down here to the 3/4 and you will see that I just kind of do it here. And you can make your squares bigger. I take the mass retained 0 divided by 2000, which would be 0, and multiply that times 100. And that gives me in a percent. The percent needs to be in whole numbers. Number. I think the same goes here too. We don't want decimal numbers over, well, I guess we do. I don't know where I got that. But anyway, 158 grams on the 3/8 is 158 divided by 2000 times 100 gives me 7.9%. Number 4 sieve, 308 grams retained on the number 4 sieve. So to get the percent, I take the weight, 308, and I divide it by 2000. I multiply that times 100 because I'm going to get a fraction here, and that will give me whole number, 15.4%. That's what I was talking about. It's going to give me a fraction. That's why we're multiplying by 100. That gives us a percent. And when we get over here, after we've got all our cumulative figured out, after we get over here, we get all of the cumulative figured out. I'm sorry. We'll, yes, get all the cumulative done, and I'm not going to do it. I want you to practice it, but
I have to go to the bathroom.
0%. Remember, the calculation for percent passing is 100 minus the cumulative percent retained. So there's nothing here. 100 minus 0 equals 100. So everything passed through the number 3/4 sieve. On this one, the 3/8, you have 7.9% in cumulative retained. 100 minus 7.9 is 92.1%. Same thing here, 23.3%. 100 minus 23.3 is 76.7%. So work through the problem. Expect to see something similar to this layout with no numbers in it. it'll have all your givens, the stuff up here, and I want you to calculate the mass retained. That'll be given. Then you calculate the percentage retained by dividing the mass by the total amount, which is upside down 2,000 grams. And that gives you the percent change. I'm sorry, the percent retained. And then again, the cumulative is like here, 0. There's nothing ahead. So you have 7.9. What it is. Now to get the cumulative, you add 0, so you have 7.9 is your cumulative. So move down to this next sieve. I'm sorry that I can't get it all on there, which would make it more comfortable, which is the number 4 sieve. It would here 3/4, 3/8, number 4, number 10, number 40, number 100, number 200, and then the pan is just, that's just everything left. So now let's look at it on the number 10 sieve. The cumulative amount was the amount retained. Let's see, where's that? The percent retained was I'm not going to go much further, am I? Yeah, where's the percent on the number 10? I want to do this one, then I'll turn it over to you. 10, on the number 10 sieve, the amount retained was 608. So I would take 608 divided by 2,000 times 100. 608 divided by 200 equals, oh, it's not on. 608 divided by 2,000 equals 0.304 times 100 equals 30.4. And that would go right here. Add this plus 23.3 equals 53.7. Cumulative percent. So there. So what I need from you guys is to go through the problem. On the test, we'll have something similar to this. Probably will be narrow it down to the ones that we will use on the graph, the number 200, the 40, the 10, the 4, the 3/8, and the 3/4. Maybe. May make you do them all again. We can pick and choose then. I don't think I want to cover anything more than that. If you need to, go back and watch those videos again. Work that problem. I want to figure out a way for you to work through this already solved problem. Show me your work. If we have room, you can do it in a text box, I believe. I have to make that an assignment, but I'm just telling you to work through that problem. Any kind of issues you have, you lose the train of thought, or if I wasn't clear on something, let's go back before we get to the assignment. You can do that through the inbox or email or whatever we want to do. If you need a complete review of this thing, I'm willing to do that. And we'll go through it again. That's quite all right. We'll make time to do it. On the assignment, though, I want to see your work, and I suggest you make your column. You don't have to. You can work this thing out any way you want to, but I want to see your column. I want to make sure that this equals, when you get through, will equal 100%. I want to see the calculations for this percent pass. And all you're doing, I know you're doing the same thing over and over, 100 minus 23.3, but I want you to be sure you know what you're doing on this, because calculating these things is really important. It can mess it, because there's more to do with this information. We'll take this percent passing right here, and this is where we'll get our plots on our grain distribution chart. So I'm going to leave it at that, and trust you will give me a holler, as they say down here where I live. If you run into problems, don't understand it, don't hesitate. And you guys, let's enjoy the week. And if you have any questions on the assignment, give me a shout. I'll try to have it up as soon as possible next week.